There are discoveries that arrive like thunder, loud enough that everyone hears them at once. And then there are discoveries that appear as a whisper inside the data, something so small that it can be mistaken for noise until the pattern begins repeating itself. The James Webb Space Telescope was built to detect those whispers. It was designed to gather ancient light from the earliest visible chapters of the universe, to push beyond the era already mapped by previous observatories, and to reveal how the first stars and galaxies emerged from darkness. It was meant to answer questions that had remained open for generations. Instead, in some of its deepest observations, it began to pose a different kind of problem. Hidden among the expected structures of the young cosmos were objects so compact, so red, and so unexpectedly intense that astronomers found themselves facing a familiar scientific sensation, the feeling that nature had just exposed a weakness in the story we tell about it. These objects came to be known as little red dots. The name sounds almost casual, as if it refers to a harmless curiosity scattered through a survey image, but the simplicity of the phrase conceals the depth of the puzzle. In astronomy, a dot is not necessarily small in any ordinary sense. It may only appear small because it is unimaginably far away, and red, in the language of the universe, does not merely describe color. It can describe time, motion, distance, dust, temperature, and history all at once. A red source in deep space may be ancient light that has been stretched to longer wavelengths by the expansion of the universe. It may also be light filtered through clouds of cosmic dust that remove the bluer part of the spectrum and leave a deeper glow behind. The challenge is that both effects can produce a similar impression at first glance, while implying very different physical realities. That is where the tension begins. Webb was expected to find very distant galaxies. It was expected to find primitive structures still in the process of forming. It was expected to see the universe in a younger, rougher state than we observe today. But some of these little red dots seem to compress too much brightness into too little apparent size. They looked too compact for normal galaxies of that era, and too luminous for simple explanations to feel comfortable. In the early universe, matter had less time to gather into massive systems. Stars had only begun to manufacture the heavier elements that later generations would inherit. The great cosmic cities we call mature galaxies should still have been under construction. Yet here were sources that seemed to suggest either rapid growth, hidden power, or a class of object not yet fully accounted for. To appreciate why that is unsettling, it helps to step back and remember what Webb is actually doing when it observes the distant universe. Light travels at a finite speed. Every time we look outward, we also look backward. The sun is seen as it was a little more than 8 minutes ago. The nearest stars appear as they were years ago. A galaxy billions of light years away is not seen in its present state, but in a state that belongs to a much earlier cosmic age. When Webb peers deep into the sky, it is not simply surveying remote territory. It is opening a record of the past. And because the universe has been expanding during light's long journey, the wavelengths of that light are stretched. Visible and ultraviolet light from the early cosmos can arrive at Webb as infrared radiation. That is why Webb sees what other telescopes could not. It is tuned to the afterglow of ancient epochs, but seeing deeper does not guarantee seeing clearly. The deeper one looks, the more interpretation matters. A distant object is faint, tiny in appearance, and stripped of context. The telescope collects photons, but the meaning of those photons must be reconstructed. Astronomers ask, is this source dominated by stars, by hot gas, by dust, or by matter falling into a black hole? Is it a galaxy spread across thousands of light years, or a compact nucleus hidden inside a larger system too faint to separate cleanly? Is the red color telling us the object is very distant, or simply buried behind dust? Every answer changes the story. At first, the little red dots could have been dismissed as a temporary ambiguity, one of those categories that appears whenever a new instrument opens a new window. But they did not remain isolated curiosities. More of them appeared. Patterns began to emerge. They occupied an important era in cosmic history, roughly within the universe's first few billion years, when the earliest large structures were taking shape. And they did something dangerous to scientific confidence. They refused to sit comfortably inside the boxes already prepared for them. They were not obviously ordinary young galaxies. They were not cleanly identifiable as known active galactic nuclei. They seemed to belong somewhere between familiar categories, and that in-between space is often where breakthroughs begin. The most immediate suspicion was that they might be powered by black holes. Not black holes in the dramatic popular sense of invisible monsters swallowing stars whole, but actively feeding black holes at the centers of galaxies. A black hole itself emits no light. The glow comes from surrounding matter. Gas pulled inward does not fall neatly in a straight line. It swirls, collides, heats, and compresses. In that process, enormous energy is released. The result can outshine the combined starlight of the host galaxy. This is called an active galactic nucleus, and it is one of the brightest known engines in the cosmos. If the little red dots were examples of such nuclei in the early universe, then their brightness would make sense. Their compactness would make sense too, because much of the visible light would come from a small central region rather than from a broad stellar disk. And yet, the black hole explanation did not immediately settle the issue. In science, a good hypothesis should not only sound plausible, it should also leave behind a trail of supporting signatures. Feeding black holes often produce energetic radiation across multiple parts of the spectrum, including X-rays. Some also generate broad emission features in their spectra, signs of rapidly moving gas close to the central engine. A spectrum is the breakdown of light by wavelength, a tool that allows astronomers to read the physical conditions of a distant object from the fingerprints embedded in its glow. The spectral clues from some little red dots did not fit the most straightforward black hole picture. Certain expected signals were weak, absent, or more ambiguous than theory would prefer. That does not eliminate black holes. It only means that if black holes are involved, they may be hidden behind thick material, operating in an unusual regime, or appearing at a stage of growth that is not well represented in nearby examples. This is what makes the discovery feel so cinematic. The mystery is not a single dramatic image. It is a conflict between possibilities. On one side stands the familiar machinery of cosmic evolution: galaxies forming, stars igniting, central black holes growing, dust reshaping what we see. On the other side stands the data, insisting that something about these objects is more compressed, more extreme, or more premature than expected. When astronomers use the word premature in this context, they do not mean impossible in any literal sense. They mean that the timeline implied by the observation pushes against the timeline predicted by current models. The universe may be telling us that some structures assembled faster than we thought, or it may be telling us that we have misidentified the engine powering them, or more uncomfortably, it may be hinting at a phase of cosmic evolution that has been largely theoretical until now. One reason this matters so deeply is that the earliest universe is not just a backdrop. It is the origin point of almost every later structure we observe. If something unusual was happening there, then the consequences could cascade forward through time. Consider the question of black hole growth. Astronomers know that very massive black holes existed surprisingly early in cosmic history. That fact alone has already strained simple models of gradual buildup. To create a giant black hole quickly, one must either begin with an unexpectedly large seed, feed it at unusually high rates, or invoke conditions that make growth more efficient than standard scenarios allow. The little red dots enter this debate like suspicious clues at a crime scene. If they are early black hole systems, then they may reveal how such rapid growth became possible. If they are not, then they may point to another mechanism entirely, perhaps one that operated before the familiar black hole-dominated phase we know from later galaxies. There is also the question of stars. The first stars in the universe were not expected to resemble stars forming today. They were born in an environment almost entirely composed of hydrogen and helium, the simplest elements produced after the beginning of cosmic history. With few heavier elements to cool the gas, the first stellar generations may have grown to extraordinary masses. Massive stars live fast and die young. They burn fiercely, shape their surroundings through radiation and shock, and may leave behind black holes that later become the seeds of larger systems. If the little red dots have anything to do with that early stellar era, then Webb may be glimpsing a bridge between the first stars and the first massive black holes, a transition so brief and so distant that previous observatories had little chance of catching it. But the universe does not make interpretation easy. Dust complicates everything. Dust is made of tiny, solid particles forged in stellar processes and dispersed into space. It is not merely a visual nuisance. It absorbs and scatters light selectively, often hiding the bluer wavelengths and allowing redder light to dominate. A galaxy rich in dust can look older, redder, or more distant than it truly is if one relies only on broad color. Dust can also trap radiation, alter temperature structures, and disguise the true nature of the central source. In nearby galaxies, astronomers have learned to read through dust by combining multiple wavelengths and physical models. In the early universe, however, those same methods become harder because the objects are faint, small, and observed across immense stretches of time. What appears impossible may sometimes be an object made ordinary by hidden dust, but there is a limit to how far that explanation can be pushed before it begins to create new problems of its own. That is why Webb's role is so critical. It does not merely provide prettier images than earlier telescopes. It changes the kind of evidence astronomers can collect. Its sensitivity in infrared light allows it to detect distant sources that were previously beyond reach. Its instruments can separate that light into spectra, revealing chemical composition, motion, and energy sources. Its resolution allows compact structures to stand out where earlier surveys might have blurred them into the background. In other words, Webb is not simply discovering the little red dots. It is making them difficult to ignore. Before Webb, such objects might have existed invisibly inside the limitations of our instruments. Now, they are present enough to force a response, and the response has been increasingly bold. Some researchers have suggested that the little red dots may represent black holes embedded in dense, unusual environments. Others have proposed that they could be linked to massive stars or to brief transitional states in early galactic development. There are even ideas that they mark a population of objects that was common for a short time in the young universe and then largely disappeared, leaving only indirect descendants behind. Each possibility carries its own implications. A hidden black hole population would transform our understanding of how quickly central engines formed. A population of supermassive stellar objects would reshape the opening act of star formation. A new transient class would imply that the young universe passed through stages not fully captured by current theory. What makes this especially gripping is that the little red dots are not dramatic because they are huge and obvious. They are dramatic because they are compact enough to conceal their nature. They sit there in the data like sealed containers, bright enough to demand attention, but closed against easy explanation. Their mystery is built not on spectacle, but on compression. Too much energy in too small a package, too much structure in too young a universe, too many examples to write off. They do not merely ask, "What am I?" They ask, "What assumptions allowed you to think I should not be here?" And this is the moment where a discovery becomes more than an observation. It becomes a test of method. Astronomers must decide how much weight to place on models built from the nearby universe when confronted by a far older cosmic environment. They must separate instrumental confidence from interpretive caution. They must resist both extremes: the temptation to force every anomaly into a familiar category, and the temptation to announce a revolution before the evidence is mature. Good science moves between those poles. It accepts uncertainty without surrendering to vagueness. It follows the clues with discipline. And in the case of the little red dots, the clues point toward one unavoidable truth. To understand why these objects feel impossible, we first have to understand how Webb sees them at all, and how a telescope built to capture ancient light turned a handful of dim red points into one of the most unsettling questions in modern cosmology. The unsettling power of the little red dots begins long before any theory is proposed for what they are. It begins at the level of detection itself, in the quiet discipline required to extract meaning from ancient light. By the time that light reaches the James Webb Space Telescope, it has already crossed billions of years of expanding space. It is weak, stretched, and detached from the conditions that first produced it. Nothing about it arrives with a label. The telescope receives patterns of photons. From those patterns, astronomers must reconstruct distance, composition, temperature, structure, and probable source of energy. That reconstruction is where the mystery sharpens, because the little red dots are not simply strange objects in space. They are objects made strange by the way they continue to behave even after the normal layers of uncertainty are peeled away. Webb was designed for this kind of work because the early universe does not announce itself in the visible light that human eyes would recognize. As the universe expands, the wavelength of traveling light is stretched. Radiation that began its journey as ultraviolet or visible light can arrive as infrared. Infrared light lies beyond the red end of the visible spectrum, and observing it is essential when studying very distant galaxies, early stars, and the gas surrounding them. This is why Webb orbits in deep space with a sun shield the size of a tennis court, and instruments kept cold enough to avoid drowning out the cosmos with their own heat. Infrared astronomy is an exercise in restraint. The telescope must be colder, quieter, and more stable than common intuition would expect, because the signal it seeks is easily overwhelmed. That engineering matters directly to this story. Without it, the little red dots would not look impossible, and they would barely look like anything at all. Earlier observatories could hint at unusual distant sources, but Webb collects more light and resolves finer detail in the infrared range that matters most for the ancient universe. It can go deeper into the sky and separate sources that would otherwise blur together. In deep field observations, where the telescope stares at a small patch of sky for long periods, objects invisible to less sensitive instruments begin to emerge from the background. Some appear as extended galaxies with discernible shape. Some appear as compact smudges, and some, like the little red dots, present themselves as remarkably concentrated points of red light that resist casual classification. At first, this may sound like an issue of image quality, but the deeper challenge is one of interpretation. A compact appearance can mean different things. It may indicate that the object is physically small. It may mean that it is a bright central region embedded in a larger system too faint to be easily seen. It may even reflect a particular stage of evolution, where energy is concentrated into a dense core rather than distributed broadly across a galaxy. Observational astronomy is full of such ambiguities. The shape seen in an image is never the end of the story. It is the opening move. To proceed, astronomers rely on a sequence of questions. How red is the object across different filters? Does its brightness change smoothly with wavelength, or are there sudden jumps and drops that indicate absorption or emission features? Is the source truly point-like or merely compact relative to the instrument's resolution? Is there evidence of surrounding diffuse light? Does its spectrum contain lines produced by ionized gas? And if so, how wide are those lines? How intense are they? And how are they shifted? A filter, in this context, is not a physical color overlay, but a carefully selected range of wavelengths observed separately, so that a source can be measured in multiple slices of the spectrum. Each filter adds another clue. The object's brightness pattern across those slices becomes a rough fingerprint of its nature. This is where Webb changes the game. It does not rely on a single view. It combines deep imaging with spectroscopy, the splitting of light into its component wavelengths. Spectroscopy is one of astronomy's most powerful tools because it turns faint glow into physical evidence. A spectrum can reveal the presence of specific atoms and ions through their characteristic lines. It can show whether gas is moving rapidly toward or away from us. It can indicate whether the energy source is dominated by hot young stars, heated dust, or matter spiraling toward a black hole. If ordinary imaging asks what this thing looks like, spectroscopy asks what this thing is doing. For the little red dots, that distinction is critical. Their redness alone could have produced many false narratives. A red object in the distant universe might simply be very far away. It might also be closer than it appears, but heavily obscured by dust. It might contain an older stellar population or a burst of active heating that reshapes the emitted light. Broad color measurements can narrow the possibilities, but only to a point. Spectra provide sharper leverage. They allow astronomers to test whether the light is dominated by stars, by gas excited to glow at specific wavelengths, or by an accreting compact object. They can also expose mismatches between expectation and reality, and that is exactly what made these objects so compelling. In some cases, the little red dots displayed broad hydrogen emission features that suggested rapidly moving gas. Hydrogen is the most abundant element in the universe, and when its atoms are excited, they emit light at specific wavelengths. In spectra, broadened hydrogen lines often imply that the gas is moving at high speeds. One familiar explanation for this is the presence of a black hole, because gas orbiting close to a massive compact object can reach extraordinary velocities. That kind of signal naturally encouraged the idea that these red sources might be active galactic nuclei in the young universe. But the story did not stay that simple. Other expected markers of conventional active nuclei proved weaker or less consistent than anticipated. Some objects looked black hole-like in one respect and not black hole-like in another. That partial alignment is exactly the kind of thing that unsettles astronomers because it implies that the usual templates are only partly relevant. Distance measurement adds another layer of drama. In the distant universe, astronomers often estimate redshift, i.e. the degree to which light has been stretched by cosmic expansion. Redshift is more than a technical number. It is a measure that connects observed wavelength to cosmic time. A higher redshift generally means we are seeing farther back into the universe's past. For many faint sources, astronomers first estimate redshift photometrically, using brightness across filters. That method can be powerful, but it carries uncertainty because dust, unusual spectra, and observational limitations can mimic some of the same color patterns. Spectroscopic redshift is more secure because it identifies specific spectral features directly. When Webb began obtaining better spectroscopic data for distant compact red sources, some of the candidates proved to be exactly the kind of early universe objects that had been suspected, but their physical interpretation remained uncomfortably open. The reason this matters is that distance controls every other conclusion. If an object is placed at an earlier cosmic time, then its brightness implies something more extraordinary. In a young universe, there has been less time for black holes to grow, for stars to enrich galaxies with heavy elements, and for large, stable structures to assemble. A compact luminous source at that epoch is more provocative than a similar source much later in cosmic history. It forces astronomers to ask not just what powers it, but how such a power source emerged so quickly. Thus, every confirmation of distance makes the problem less abstract and more urgent. Even size estimates become treacherous in this regime. A distant source that appears point-like is measured against the limits of the telescope's resolution, and that means astronomers must model what a true point source should look like in Webb's optics. Only then can they decide whether the object is unresolved, barely resolved, or slightly extended. This sounds dry, but it is central to the tension. If the little red dots are truly unresolved or nearly so, then whatever dominates their light is packed into a tiny region. If they are subtly extended, then stars in a compact galaxy might be responsible. If there is a bright core plus faint outskirts, then a mixed picture becomes possible, perhaps a central engine wrapped in a small host galaxy. Tiny differences in the shape of the light profile can shift the whole physical interpretation. There is also the issue of dust re-radiation. Dust grains absorb energetic light and re-emit it at longer wavelengths. In practical terms, this means that a hidden energy source can appear transformed by the material around it. A buried black hole may lose its harshest signatures while retaining a reddened infrared presence. A dense burst of star formation can also heat dust and create a red luminous object whose true internal structure is hard to infer directly. Distinguishing these scenarios requires careful modeling, and modeling always carries assumptions. How much dust is present? What is its temperature? How is it distributed? Is the source viewed face-on or through thicker obscuring layers? These are not trivial details. They are the difference between an early black hole growth channel and an extreme stellar system. This is why the phrase, "Webb sees the impossible," is more than poetic framing. The telescope is not witnessing impossibility in a theatrical sense. It is witnessing combinations of observational properties that strain easy interpretation. Compactness suggests one kind of source. Redness suggests another. Broad spectral features hint at a third. Missing corroborating signals pull the analysis back again. The effect is cumulative. Each new piece of data should make the object simpler. Instead, in many cases, it makes the object more specific and more puzzling at the same time. Or there is a common misunderstanding that better instruments simply erase ambiguity. In reality, they often relocate it. A low-quality image leaves many broad uncertainties. A high-quality observation removes some of them, but can reveal a deeper contradiction underneath. Before Webb, one might have imagined the early universe in relatively smooth categories: primitive galaxies here, active nuclei there, gradual black hole growth in the background. Webb has not destroyed those categories. It has complicated the boundaries between them. The little red dots exist inside those boundaries like pressure points, forcing astronomers to ask whether the categories themselves were too clean. And there is an emotional shift that happens when a telescope stops confirming expectations and starts creating categories of its own. Science thrives on prediction, but it advances through the encounter with the unpredicted. The first response is always caution. Calibration must be checked. Selection effects must be understood. Bias in the observations must be accounted for. Are we seeing only the brightest examples because fainter relatives escape detection? Are the color criteria favoring unusual dusty sources over more ordinary galaxies? Could line emission make the objects appear brighter in certain filters, distorting estimates of their mass or age? Every one of these questions has to be asked before a mystery can earn its seriousness. The little red dots passed that threshold not because they were instantly understood, but because they remained interesting after those basic skeptical tests began to be applied. As the data improved, the narrative changed from "look at this strange red source" to "why is there a whole population of them?" That transition is profound. A single anomaly can be due to chance, contamination, or a rare configuration. A population suggests an environment, a process, or an era. It suggests that the young universe may have routinely produced compact luminous red objects for a period long enough that Webb can now sample them. Once that possibility enters the discussion, the implications widen. These objects are no longer curiosities at the fringe of an image. They become candidates for a missing chapter in cosmic evolution, and that missing chapter sits at the crossroads of several great questions. How did the earliest black holes become so massive so quickly? What did the first generations of stars actually look like? How much dust could the young universe build earlier than expected? How often did galaxies pass through short, violent phases before settling into forms more recognizable today? Webb's instruments do not answer those questions with a single observation. They sharpen them into a shape that can no longer be ignored. By now, the little red dots are no longer just red points in a deep field. They have become a test case for the telescope's deepest promise. not merely to see farther, but to reveal the physical mechanisms hidden within that distance. And once the observational evidence is taken seriously, once the imaging, spectra, redshifts, and size constraints are laid side by side, the mystery narrows to a far more dangerous question. If these objects are real members of the young universe, and if their light is truly as concentrated and unusual as it appears, and then something in that early cosmos was building compact power sources with startling speed. The next step is to decide what kind of engine could do that, and why two radically different explanations, monster stars or hidden black holes, now stand at the center of the argument. By the time the little red dots had survived the first rounds of observational scrutiny, the mystery had narrowed into a more dangerous and more revealing form. It was no longer enough to say that these objects were compact, distant, and unusually red. The real question had become what engine could produce those qualities together in that era of cosmic history, without leaving behind a cleaner signature of its identity. Two possibilities began to dominate the discussion. The first was unsettling, but familiar. Perhaps these were black holes growing behind veils of dense gas and dust, and concealed just enough to evade the standard diagnostic signs astronomers usually rely on. The second was far more disruptive. Perhaps Webb was catching sight of a stellar phase so extreme that it blurred the line between star cluster, proto-galactic core, and the seed of a future black hole. In other words, the telescope may not simply have found a strange object. It may have stumbled into a missing transition in the early universe. The black hole interpretation has an obvious appeal because black holes solve a major part of the luminosity problem almost immediately. When matter falls toward a black hole, gravitational energy is converted into heat and radiation with extraordinary efficiency. A relatively small region can shine with astonishing power if enough gas is being funneled inward. This is exactly why active galactic nuclei are among the brightest persistent sources in the universe. They can dominate the light of their host galaxies and remain compact in appearance because the most intense emission comes from close to the central gravitational well. If the little red dots are powered by accretion, much of their puzzling brightness can be explained without demanding a galaxy-wide burst of star formation compressed into a tiny volume. But a good explanation in astrophysics must do more than reproduce brightness. It must also explain the detailed texture of the light. A feeding black hole usually leaves multiple clues behind. Gas close to the center may move at such high speeds that spectral lines become broadened. More distant gas can be illuminated and ionized, creating additional emission features. X-rays may be produced in the hottest inner regions. The surrounding dust may absorb some of that energy and re-radiate it at longer wavelengths. In other words, a black hole does not merely shine, it creates an entire physical environment, and that environment often betrays its presence through a recognizable combination of signals. The problem with the little red dots is that their evidence appears simultaneously suggestive and incomplete. Some of them show broadened hydrogen features that tempt astronomers toward the black hole interpretation. Broadening, in this context, means that the emitted light is spread across a range of wavelengths wider than it would be in a calm gas cloud, usually because the emitting material is moving very rapidly. That kind of motion could indeed arise close to a massive compact object, yet other expected signatures are not always there in the proportions many models would predict. Certain chemical emission lines can appear weak. High-energy conformation is often elusive. The whole picture begins to resemble a black hole that is present but heavily muffled, as if the central engine exists inside a thick cocoon that lets only part of its story escape. That cocoon scenario is physically plausible. The early universe was not a clean laboratory. Gas could gather densely in the centers of young galaxies. Dust, although less abundant at the earliest times than in later cosmic history, could still form surprisingly quickly through the lives and deaths of massive stars. In such an environment, a growing black hole might be hidden inside layers of material that absorb and reshape the emerging radiation. X-rays could be suppressed. Optical signatures, if shifted into the infrared by distance, could be further diluted or altered by reprocessing. What emerges would not look like a textbook nearby active nucleus. It would look stranger, redder, and perhaps more compact than the examples astronomers know best from the more mature universe. And yet even that version of the explanation raises its own difficulty. If these are hidden black holes, then they imply a population of black holes that formed early and grew quickly enough to become observationally important within a very short cosmic interval. That is not impossible, but it is far from trivial. Massive black holes are thought to begin as seeds, and the size of those seeds matters enormously. A small seed formed from an ordinary stellar collapse must grow aggressively to reach large masses early in cosmic history. A larger seed formed through more direct collapse could shorten the timeline, but then one must explain how the necessary conditions arose so often. Thus, the little red dots do not merely ask whether black holes are present. They ask what kind of black hole ancestry the young universe allowed. This is where the alternative becomes both thrilling and unsettling. Some researchers have proposed that at least some of these sources may not be ordinary black hole systems at all, but extremely massive stars or star-like structures in a brief, unstable state. To understand why that idea exists, one has to leave behind the modern stellar imagination for a moment. The stars around us today form in gas that has been enriched by countless earlier generations. That enrichment matters because heavier elements help gas cool and fragment. When gas cools efficiently, it tends to break into smaller clumps, and smaller clumps produce more ordinary stellar masses. In the early universe, before many generations of stars had enriched their surroundings, gas composition was far more primitive. Under such conditions, some theoretical models suggest that much larger stellar masses could form. A supermassive star in this context does not mean merely a large star by the standards of today. It means an object so extreme that it becomes a bridge between stellar physics and black hole physics. Such a star could be overwhelmingly luminous, radiating intensely while remaining compact on galactic scales. It could exist only briefly before collapsing under its own gravity. If objects of that kind formed in the early universe, they would be natural candidates for producing large black hole seeds. They would also represent a phase of cosmic history that astronomers have long suspected might exist, but have never observed directly with confidence. The little red dots are intriguing, partly because they seem to sit right where such a phase might reveal itself. The appeal of the monster star interpretation lies in how elegantly it addresses the problem of timing. A supermassive stellar object forming directly from pristine or nearly pristine gas could bypass some of the slower steps in the normal pathway from small star to black hole to massive black hole. Instead of starting tiny and growing gradually, nature could begin with something already enormous and unstable. Collapse would then generate a comparatively heavy seed, making the later emergence of large black holes less surprising. In narrative terms, this would mean that Webb has not merely found an odd class of luminous red source, it has found the missing opening move in one of the universe's most difficult growth stories. But here, too, the evidence must be handled with restraint. A supermassive stellar interpretation is exciting precisely because it fills a theoretical gap, and that is also the danger. Scientists are always tempted by explanations that solve multiple problems at once. The challenge is to distinguish an idea that is beautiful from one that is necessary. Could an extreme stellar object reproduce the observed spectral behavior? Could it explain the broad lines without invoking a black hole-dominated accretion environment? Could it account for the redness through a combination of temperature, distance, and surrounding material? Could enough such objects exist to create a population rather than a few isolated rarities? These are not decorative questions, they are the entire test. There is also a subtler possibility that complicates the clean opposition between monster stars and hidden black holes. The universe may not be choosing one over the other. Some little red dots may represent objects in transition. A massive stellar system could be on the verge of collapse, already shaping its surroundings with intense radiation and outflow, while a central black hole either has just formed or is about to form. In that case, the object would carry mixed signatures. Part of its light would look stellar, part would look accretion-powered. Some expected black hole indicators might still be weak because the central engine is embryonic or deeply buried. What Webb would then be observing is not a category, but a process, a transformation caught in motion. That possibility is both scientifically appealing and observationally maddening. Astronomy usually works with snapshots. Even when we say we are observing evolution, we are often assembling it from many separate objects caught at different stages. The little red dots may be forcing exactly that kind of reconstruction. Perhaps some are compact, dusty starbursts, systems where stars are forming at an extreme rate inside a small region. Perhaps some are newly awakened black holes. Perhaps some are brief pre-collapse stellar giants. The category may not be pure because the underlying cosmic moment was not pure. The young universe was likely full of violent thresholds, with gas clouds collapsing, stars igniting, radiative feedback pushing outward, black holes emerging, and dust beginning to veil the whole scene. Webb may be revealing that the early cosmos did not progress through neat labels, but through overlapping states. If so, then the discomfort astronomers feel is understandable. Modern astrophysics prefers classification because classification makes statistics possible, and statistics are how populations become history. But a transitional population is harder to count cleanly. It may occupy the observational space between established categories. It may mimic one thing in color, another in spectrum, and another in physical size. That is exactly the behavior that makes the little red dots so important. They are not mysterious simply because they are far away. They are mysterious because they may expose the weakness of our categories when applied to the earliest cosmic environments. The black hole camp and the monster star camp are therefore not just competing over one set of objects. They are competing over the opening architecture of the universe. If hidden black holes dominate, then early black hole growth was already underway on a remarkable scale, perhaps in dust-obscured phases that previous telescopes could not see. If supermassive stellar objects dominate, then the first great gravitational collapses may have begun with stars far more extreme than standard intuition allows. If the truth is mixed, then the early universe may have been even more dynamic than either side alone captures, producing compact luminous systems that moved rapidly from one physical regime into another. There is another reason the stellar interpretation remains alive, despite the gravitational pull of the black hole hypothesis. Black holes are conceptually convenient. They are powerful, compact, and capable of explaining luminosity efficiently. But convenience is not proof. If one leans too heavily on black holes, one risks turning them into a universal solvent for every difficult observation. The history of astronomy warns against that habit. Many cosmic puzzles eventually prove more nuanced than the first compact object explanation suggests. Sometimes the hidden variable is dust. Sometimes it is geometry. And sometimes it is a short-lived evolutionary phase barely represented in nearby galaxies. And sometimes it really is a black hole, but one embedded in conditions unlike anything we have yet observed locally. The point is not to resist black holes for the sake of novelty. It is to demand that the evidence earn them. In practical terms, the next stage of the argument depends on tightening the links between observation and physical modeling. More precise spectra can help determine whether gas motions are consistent with stellar winds, collapsing envelopes, or accretion-dominated inner regions. Better constraints on surrounding dust can limit how much radiation is being hidden and reprocessed. Surveys of larger samples can reveal whether little red dots occupy a narrow range of cosmic time, which would favor a transitional interpretation, or whether they appear across a broader interval, which might suggest a more stable underlying class. Each new object becomes a vote, but only if measured carefully enough. And all the while, the emotional center of the mystery remains the same. Webb seems to be showing us engines that are too concentrated and too early for comfort. The telescope does not yet tell us whether those engines are buried black holes, collapsing stellar giants, or a sequence that moves from one into the other. What it tells us is almost more unsettling. The young universe may have been manufacturing compact sources of extreme luminosity in ways we do not yet understand. That is not a small correction to an established picture. It is a pressure crack running through the foundation, because once the possibility is admitted that the little red dots are not marginal oddities, but evidence of a common early phase, the consequences expand beyond their own identity. They begin to touch the origin of the first quasars, the speed of galaxy assembly, the production of dust, the seeding of heavy black holes, and the pace at which the young cosmos matured. In other words, the fight over what these red points are becomes inseparable from a larger and more consequential question. If this interpretation holds, what else in our account of the early universe has to change with it? If the little red dots turn out to be real signposts of a common phase in the young universe, then their importance extends far beyond the objects themselves. A discovery like this does not stay contained inside one corner of astronomy. It begins to push outward, touching every larger story connected to it. The formation of the first galaxies changes. The growth of the earliest black holes changes. The timeline for chemical enrichment changes. Even the emotional architecture of cosmology changes, because a universe that assembles complex, compact, luminous structures earlier than expected is not merely a universe with one surprising data set. It is a universe whose opening act was more efficient, more volatile, and perhaps more creative than the simplified versions of our models had allowed. That word, efficient, matters. In astrophysics, the deepest arguments are often arguments about time. There is only so much time available between one cosmic milestone and the next. If a large black hole exists very early, astronomers ask how enough matter reached it quickly enough. If dust is already abundant in a young galaxy, they ask how the stars that make the ingredients of dust lived and died quickly enough. If a compact galaxy appears mature, they ask how gas cooled, condensed, ignited into stars, and organized itself rapidly enough. The little red dots press on this pressure point from multiple directions at once. Whatever powers them seems to imply that certain processes in the early universe were moving at a speed or under conditions that our most comfortable assumptions did not fully anticipate. Take the question of black holes. Long before the little red dots became a serious subject of debate, astronomers were already struggling with the existence of extremely massive black holes in the early universe. Some of these objects appear in the form of quasars, brilliantly luminous sources powered by accretion onto black holes that had somehow reached enormous masses while the universe was still young. The problem was never that black holes exist. The problem was how they grew so fast. A small seed left behind by the collapse of an ordinary star can grow only at a limited pace, unless conditions are almost continuously favorable. Interruptions matter. Radiation produced during accretion can push gas away and slow the feeding process. Mergers can help, but they require structures to exist in the first place. The early appearance of giant black holes therefore forced theorists to imagine either unusually massive seeds, unusually efficient growth, or both. Now, place the little red dots into that older puzzle. If even a fraction of them are hidden black hole systems, and then they may represent the obscured growth phase that standard observations were missing. In that picture, the universe may have been producing a large population of rapidly feeding black holes wrapped inside dense gas and dust, visible to Webb precisely because its infrared sensitivity can penetrate parts of that shrouded environment. That would be a major shift. It would suggest that the path to early quasars was not dominated only by rare exposed beacons, but by a broader concealed population building mass in the dark, or at least in a redder, more hidden phase than earlier telescopes could capture. The consequence would not be limited to one interpretation. It would alter population counts, growth models, and the expected relationship between early galaxies and their central engines. But the implications become even more radical if the monster star interpretation proves even partly correct. Imagine that the early universe could, under the right conditions, produce supermassive stellar bodies or star-dominated cores that were not simply oversized versions of modern stars, but transitional structures on the edge of catastrophic collapse. Such objects would offer a direct route to large black hole seeds. Instead of beginning with a modest remnant and then demanding near miraculous growth, nature could start with something already extreme. That would relieve one of the great tensions in early black hole formation. It would not solve every detail, but it would change the first step so dramatically that the later steps become easier to understand. In narrative terms, it would mean the universe opened its black hole story not with a whisper, but with a very large first move. And that first move would have consequences for galaxies too. Galaxies are not passive containers. Their histories are shaped by the stars they form and the compact objects they grow. Massive stars pour energy into surrounding gas through radiation, outflows, and explosive deaths. Black holes can do the same through jets, heating, and the broader influence of accretion. These feedback processes matter because they regulate further growth. They can compress gas in one place while clearing it out in another. They can trigger star formation or suppress it. They can enrich the surrounding medium with heavier elements and redistribute matter across the young galaxy. If the little red dots mark a phase where extreme compact sources were common, then the feedback environment of the early universe may have been more intense and more localized than many models assume. Galaxies may have been sculpted from the inside out earlier than expected. This also affects the history of chemical enrichment. The earliest universe began with almost no heavy elements. Hydrogen and helium dominated. Everything else had to be forged later inside stars and released into space. Dust, too, had to be manufactured. Yet some distant objects observed by Webb already appear more chemically evolved or more dust-rich than a simplistic picture of the early universe would suggest. The little red dots sit inside that wider surprise. If they involve massive stars, then they may point to an environment where enrichment happened quickly. If they involve buried black holes inside dense central regions, then they may indicate that young galaxies were already building complicated internal conditions sooner than anticipated. Either way, the idea of a uniformly primitive early cosmos becomes harder to maintain. Webb's universe is not merely young. In places, it appears unexpectedly developed. That does not mean cosmology is collapsing. It means something more interesting. The broad framework remains strong. The universe expands. Light is redshifted. Structure grows through gravity. Stars manufacture heavier elements. Black holes feed and evolve. None of that is being overturned. What changes is the timing, the efficiency, and the sequence. Science advances most often through that kind of revision. The deepest theories survive, but the details become less comfortable and more precise. The little red dots matter because they operate exactly at that level. They are not evidence that the universe is broken, and they are evidence that our shorthand version of the early universe may have been too neat. This is why discoveries like this create such a powerful mixture of caution and excitement. Caution is necessary because the young universe is a difficult place to observe. Distance creates faintness. Dust creates disguise. Selection effects shape what we detect. The most luminous objects are easier to find, which can make the early universe look more dramatic than it was on average. Rare phases may be overrepresented because ordinary faint systems fall below the detection threshold. Models depend on assumptions about geometry, composition, and orientation. Every conclusion must survive those uncertainties. Excitement remains justified because even after those caveats are acknowledged, the pattern persists. Webb is repeatedly showing us early sources that feel denser, brighter, dustier, or more mature than simple expectations would predict. The little red dots belong to that family of surprises, and they are not alone. One of the most important things about Webb's first years is that the telescope has not produced a single isolated anomaly. It has produced a cluster of related tensions. There are galaxies that seem unexpectedly bright at early times. There are structures that appear more organized than expected. There are possible signs of rapid black hole growth and strangely efficient star formation. Each observation on its own can be debated. Together, they begin to suggest a theme. The young universe may have been more capable of building concentrated complexity quickly than astronomers had appreciated. The little red dots are powerful precisely because they condense that theme into a single visual class: tiny, red, intense, and temporally inconvenient. The phrase temporally inconvenient may be the most honest summary of why they matter. They force timing problems into the open. They ask whether gravity assembled central concentrations faster. They ask whether gas collapsed more efficiently under low metal conditions than models assumed. They ask whether the first stellar generations were more extreme, whether dust accumulated more rapidly, whether black hole seeds started larger, or whether all of these things were interacting in a more coordinated way than the field has yet captured. Once those questions are on the table, the discovery stops being about one object class and becomes a referendum on our confidence in the early stages of structure formation. There is also a philosophical consequence. Astronomy has always moved by extending the senses. Each new instrument does more than sharpen a picture. It changes which parts of reality are accessible enough to become scientific facts. Before the telescope, planets were wandering lights. Before spectroscopy, stars were points without chemistry. Before radio astronomy, the sky had no invisible weather. Before X-ray astronomy, black hole environments were largely silent. Webb belongs to that lineage, and the little red dots are an example of what happens when a new instrument reveals not just more of the known, but a population that sits awkwardly between known categories. In hindsight, if these objects prove central, future astronomers may look back and wonder how our picture of the early universe ever seemed complete without them. And that is the mark of a significant discovery. At first, it appears optional, a specialist debate carried by technical papers and cautious conference talks. Then, slowly, it becomes structural. Textbooks start adjusting. Simulations are rewritten to test new seed masses, new dust histories, new collapse pathways. Observers build targeted surveys. Spectroscopic campaigns become more ambitious. Competing teams argue not about whether the objects matter, but about which mechanism dominates them. Eventually, the discovery migrates from anomaly to chapter heading. We do not yet know whether the little red dots will complete that journey, but they already possess the one quality that major discoveries always possess at the beginning. They make older stories feel provisional. The future of this mystery will depend on accumulation. More objects must be measured. More spectra must be taken. More wavelengths must be compared. Theorists must keep testing whether hidden black holes, supermassive stars, extreme starbursts, or transitional hybrids can reproduce the data without creating new contradictions. Some explanations will likely fail. Others will combine. The final answer may turn out to be less singular than audiences prefer. Nature often works that way. The class called little red dots may contain multiple physical realities that happen to converge in appearance. But even that outcome would be revealing. It would tell us that the young universe repeatedly generated compact red luminous systems through several channels, each one feeding the larger architecture of cosmic growth. And perhaps that is the most compelling possibility of all. The impossible thing in deep space may not be one impossible object. It may be an impossible density of beginnings, a phase where stars were becoming black holes, where black holes were becoming galactic engines, where galaxies were learning to organize themselves, and where dust was already beginning to curtain the violence from direct view. Webb, with its patient infrared gaze, may have arrived just in time to catch the traces of that phase before distance and expansion diluted it beyond reach. If that is what we are seeing, then the title that sounded like exaggeration at the start becomes something more disciplined and more profound. James Webb did not literally find something impossible. It found something that feels impossible only because our previous picture of the young universe was too small for it. The little red dots may be telling us that the early cosmos did not spend its youth slowly becoming interesting. It may have become dangerous, efficient, and structurally ambitious almost at once. And if that is true, then these faint red points are not footnotes in the story of the universe, when they are the moment where the first chapter stops looking like a calm beginning and starts looking like a race already underway. That is why the mystery matters, even before it is solved. It reminds us what a telescope is really for, not to decorate what we already believe, but to expose where belief has outrun evidence. Webb was sent into space to look back toward the beginning. In doing so, it may have found not a finished answer but the outline of a hidden era, compact, red, luminous, and unresolved, waiting for us to admit that the early universe was stranger, faster, and more inventive than we were prepared to see. And once that admission is made, the dots are no longer small. They become thresholds. Beyond them lies a version of cosmic history still being written,